use the Fourier series properties to evaluate the Fourier coefficients for arbitrary waveforms. So instead of using directly the Fourier analysis equation to evaluate the Fourier coefficients, we're going to use the Fourier series properties to our convenience. Okay, so this is example 3.6 from your course text, and it says what it has is a signal GT with a fundamental period of 4, which is shown in the figure below. So you can see this, the period is 4. Okay, this is a square bipolar square waveform, which has a period from one period time taken from -2 to +2. So the period is 4. Okay, and this pattern goes on repeating. It's a periodic square waveform. So what we can do is either we could determine the Fourier series representation of GT directly from the analysis equation. So if for GT, now for this GT, let's say the Fourier coefficients are represented by Bk, where K are the harmonics, K is the harmonic index. You can go on and evaluate the Fourier coefficients directly using the Fourier analysis equations over one time period, which is 4. So this is T, capital T. You can evaluate the Fourier coefficients directly. Okay, all you need to do is to have the Fourier coefficient, so you can express this in terms of Fourier series. So this is GTE minus J K omega naught is 2 pi by T. It can be written as such. So let's have it as 2 pi by T divided by T into small t dt. Okay, this is the direct Fourier analysis equation, which gives you the Fourier coefficients. Okay, and if you have them for GT, then you see you can express GT as you can expand GT in terms of the Fourier series as a summation. Okay, summation is over K over the harmonic index into Bk. Then you have Bk's, if you recall. Then you have E to the J K 2 pi by T. Okay, same thing. The period is T into T. Okay, so all you need to do is to find the Fourier series coefficients. Okay, and with these Fourier series coefficients, again, they are finite, for which the series is convergent. You just plug these Fourier coefficients in your Fourier synthesis equation. So this is analysis equation. Okay, this is the analysis equation, which gives you the Fourier series coefficients. Okay, and then you have the Fourier synthesis equation. So this part is the synthesis equation. So all we need to find out is the Fourier coefficients. Now either you can use this integration in the Fourier analysis equation to find the Fourier coefficients Bk, or instead you can use the relationship of GT to a symmetric periodic square wave xt, which we have already seen in example 3.5, and for which this is xt. Okay, and by definition xt is 1. You can see it's 1 for minus t1 to plus t1, and this is 0 otherwise. So this is again periodic with period capital T. So we know what the Fourier series coefficients are, and last time in the last video you can see how we determine the Fourier series coefficients, AK is for this. So we know what AK is, right? Now the idea is, instead of directly employing the analysis equation, let's try to exploit the relationship between GT and XT. Okay, and see how we can use the Fourier series property to our convenience. Okay, so referring to this to that example, now we can see that T equal to 4, the period, because the period is 4 for GT, the period is 4, and T1 becomes 1. Okay, so if you are going to refer to these two periodic signals and going to express GT in terms of XT, then just look at this equation. GT is XT minus 1 over 2. What it means is that, okay, now XT minus 1 will be a shifted pulse. It will be a shifted pulse. So okay, so it will be, so this is, let's say, minus T1, then 0. Okay, that's not true. Then T1. So then we have this from minus T by 2 to T by 2. Okay, so I'm just going to replot the expression for first let's have for xt minus 1, So before we had this pulse like this, right? So this is your xt, this is your xt, right? So if you're going to shift this by 1, okay, where t1 is 1, so this is basically 1, and then you have again this is also 1, and capital T is 4, so this is minus 2, and this is again plus 2. Okay, So xt minus 1 is going to be shifted, will be a shift towards right, by uh, 1 second. Okay, so this is this solid line. This solid line represents xt minus 1. Okay, this is xt minus 1, and this is your xt. This is your original xt. Okay. Now, if I'm going to subtract half from this signal xt minus 1, then this will take the form like this. This will become like this, and then there will be a half subtraction. So over this time period, it will take like this. The amplitude will be minus half. So minus half and plus half, like this. So this thick red curve, the thick red curve, is showing you xt minus 1, xt minus 1, minus half. Okay, this is xt minus 1 minus half. And if you can compare this curve with this curve, these are the same. Okay, so gt can be expressed as xt minus 1 minus 1 over 2. I mean, the motivation to write this in terms gt in terms of xt is that we are going to use the Fourier series properties to evaluate the Fourier coefficients for gt instead of directly using the analysis equations. Okay, so now you can see the first thing to notice is that now all we know right now is that, okay, if you have a signal xt, then we have the Fourier series coefficients which are given by ak, right? And if you recall last time in the properties, if your signal is shifted by, let's say, there's a shift to right by t0 time period, then the Fourier series coefficients, they take the form of e to the minus j k omega naught t naught. Okay, t0 is the same shift by which the signal is shifted, okay, multiplied by ak. So if you look at this case over here, gt, then gt will, if gt has a Fourier coefficients of bk, let's call them bk. Okay, we don't know what bk is, and we are going to use AKs instead for evaluation of direct evaluation of BK. So BK will be, from linearity, will be e to the minus j k omega naught. Since t naught is 1, so this is 1, and then AKs. And then you need to do something about this DC term. Okay, this is a DC term, so DC is a constant quantity, so there won't be any harmonics. Okay, so you can write this as, so this is for k not equal to 0, for k not equal to 0. For DC term, you can write this as, well, bk will take the form of a naught. A naught is the DC Fourier coefficient of, or the average of xt, minus half, right? I mean, so this is for k equal to 0. Because from linearity, you have to evaluate the Fourier coefficients first for xt minus 1, which is this part, okay, and then you have to take care of the DC term as well, minus half. And you recall, if I mean, this is straightforward. I mean, this, if you have to just substitute over this over minus 1 over 2, find the Fourier coefficients. This is just a DC term dt, and this average has to be taken over 1 over t. Well, this gives you back minus 1 over 2, which is again DC. Okay, so that's the DC term which is contributing a constant in GT. So, but then this is not the complete story. There are DC. There's a DC Fourier coefficient, or DC term, which is also in xt, which is also there in xt. So you have to take care of that. That's a naught. Okay. So for k equal to 0, we have a naught minus 1 over 2. So you see, all we did is, we know that xt has a Fourier coefficient of ak. So xt minus t naught will have the Fourier coefficient of e to the minus j k omega naught t naught, which we derived in the Fourier series property. Okay. And for this term, well, we had this for xt minus 1. So for xt minus 1, this simply becomes e to the minus j k omega naught ak. That's it. And then by linearity, since there are two terms, you can use, if you expand the Fourier analysis equation in terms of two or more linear combination of such signals, you can go on bifurcating or trifurcating your integrals, right? So by linearity, since there are two terms, so there will be two, again, two such Fourier coefficients. So one is the DC term. So the DC Fourier the DC is minus half, okay? And the other DC is coming from the signal X. So you just add them up. A naught minus 1 over 2 is for k equal to 0. For k not equal to 0, this is the story, okay? This is the story. So that's it. We have determined the, so all now you need to know is AKs, which are already determined in example 3.5. So let's go on substituting that, okay? So here, it's just the same thing which I've said. So the time shift property indicates that if the Fourier series coefficients are denoted by AK, then xt minus 1 can be represented as such, okay? So if you use this property, then this is nothing but e minus jk 2 pi by t. T is 4, so just substitute that e minus jk pi by 2, or you can keep this omega naught if you so desire. The DC off time for minus 1 over 2 is itself is minus 1 over 2 for k equal to 0, and there is no harmonic. I mean, it's 0 for k not equal to 0. It's a DC term. So gk is of the form. These are the Fourier coefficients for the signal gt, right? So for the signal, this is the signal gt over here, which we have expressed in terms of xt. Okay, so I was writing this as bk. Now you can have this as gk as well. I mean, just for the sake of convenience, which is expressed over here as in terms of gk, not bk's. Then, since ak was derived as such, you can just substitute this for a naught. For example, a naught is half over here. Then substituting a naught half means that the DC term is 0, right? Which is quite evident. If you look at GT, the average of this signal, well, the average of this bipolar square pulse square waveform is 0. The DC is 0, right? You can see the DC is 0, which simply means, okay, GT dt over one period is 0, right? This integral is 0. That was expected. But we have done this indirectly, not directly. Okay, so this is a DC term. Because there was another DC in A naught as well, which is of the form 2T1. Well, the DC for this term, if you recall from example 2.5, was 2T1 or capital T. And here, if you see, capital T is 4, and 2 by 4 is 1 half. T1 is 1, so this is 1 half. Okay, so the DC term becomes 0 if you combine the DC terms of xt and half over here. Becomes 0, okay? So that was expected. So for k equal to 0, this is 0. Now if you substitute ak over here, this term comes over here together with e minus jk pi by 2, which is coming from here. Where is it? Yeah, here. This is e minus jk pi by 2 because of the shift, and then this is multiplied by ak. So this is, you see, we have not used directly the Fourier analysis equation. We have employed the Fourier series properties to evaluate the Fourier coefficients GKs. Okay, so let's take another example. This is example 3.8 from your course text, and what it says is to examine some properties of Fourier series representation of periodic train of impulse or impulse train. So this impulse train with period t can be expressed as such. Okay, and a visual of this is shown in this figure. Okay, so xt is written as a summation of impulses. So for k equal to 0, it's just a delta t function. Okay, at 0, and this is for k equal to 0. When k is equal to 1, then at plus minus t because k is varying from minus infinity to plus infinity, then at plus minus t you will have an impulse, then plus minus 2t, plus minus 3t. Okay, so this is a periodic impulse train. Okay, having period from having a period of capital T. So let's say from minus t by 2 to plus t by 2. This is one period. Okay, so this is illustrated in the figure below. To determine the Fourier series coefficients ak, we use the Fourier analysis equation and select the interval of integration to be minus t by 2 to plus t by 2. That is one period, right? So to determine the Fourier coefficients, you can use this. You can just plug for xt over here, multiply by e minus jk omega naught t. Omega naught is 2 pi by t. Okay. Now you notice that from minus t by 2 to plus t by 2, that's over one interval, one period. K is 0. Okay, over this period there's only one impulse that I can see. Okay, there's no other impulse, so K is 0. If you substitute for K equal to 0, the summation vanishes. You're left with delta t, and you know the area under direct delta function is 1 over t. Okay, so what we have done is we have avoided the placements of impulses at the integration limits. So within the integration limits from minus t by 2 to plus t by 2, within this interval, there is only a single impulse, so that is delta t. Okay, and delta t multiplied by e to the minus j omega naught t, by shifting property, delta t only exists at t equal to 0. Okay, so this will be for t equal to t is 0 over here, and you have k over here. So this simply means this is ej0 is 1. Okay, so delta t in dt is 1 over t, right? Okay, so one other thing to note over here is that xt is both real and symmetric. Okay, so ak's are 1 over t for all k. Okay, so for all harmonics, this is 1 over t, right? And you can say that well, ak's are even. Okay, that is a minus k is a plus k. Over here you can see that. Okay, a minus k is a minus k. And that was expected. Okay, because your signal is symmetric, therefore the Fourier coefficients are symmetric. Okay, and it's also even. The signal is also even. X minus t is x plus t, right? X minus t is x minus t is xt, which means the signal is even. Therefore, the Fourier coefficients are also even. So xt is both real and even. Therefore, the Fourier coefficients are also both real and even for all k. Okay. So, in other words, you can also say the Fourier series coefficients of this impulse train are all identical. This is 1 over t. So, these coefficients are real valued and even with respect to index k, because this is to be expected since any real and even signal such as our impulse train should have real and even Fourier series coefficients. Okay, so actually we have shown this for before as well. So if you are going to flip the signal, instead of ak, you are going to have a minus k. Okay, but for real and even signals, the Fourier coefficients also turn out to be real anyway. If it was an odd signal, then the Fourier coefficient would also have been odd. Okay, and real if the signal was real again. So that's the story. I mean, that's how the properties are. So now the impulse train also has a straightforward relationship to square wave signals. So now we are going to evaluate the Fourier coefficients indirectly by exploiting the relationship of impulse with the square wave signal. So such as GT as shown in figure below. So GT is again a square wave, okay, and it's periodic. And this is one period. So minus t by 2 to plus t by 2. This is one period, that is capital T, okay. And the derivative of GT is the signal QT is illustrated in the bottom of the figure. So the derivative is going to consist of the impulses like this. So at minus T1 and then at plus T1 like this. Okay, and this trend continues or at plus minus T as well. Okay, this is minus T, and then at plus minus 2T you're going to have such impulses. So we may interpret QT as a difference of two shifted versions of the impulse train, that is xt plus T1 minus xt minus T1. So this is, if you recall, this was your xt, and xt plus T1 simply means that your impulse is shifted at minus T1 and x. So this term is over here, right? And this term is implying a negative, basically having a negative strength impulse at plus T1. Okay, so it's basically, I mean, you can first of all there's a relationship between the square waveform and the impulse, that is you take the derivative, so you have QT. Okay, so basically d by dt of GT is your QT. This is your QT, and then you can express QT in terms of a difference equation in terms of x, which is over here. Okay, and this x is your impulse train itself. Okay, so you can just shift it from minus T1 to plus T1, and then you can construct a periodic shifted impulse train. So using the properties of Fourier series, we can now compute the Fourier series coefficients QT and GT without any further direct evaluation of the Fourier series analysis equation. So first, from the time shifting property and linearity properties, the Fourier series coefficients BK of QT may be expressed in terms of the Fourier series coefficients A of xt. So that is, so now we know what is AK is, okay. AK, so for xt, we have the Fourier coefficients AKs, okay, which are identical for all k. So for xt, we have the Fourier coefficients AK, which is 1 over t, which we have evaluated before. So this is 1 over t. So this Fourier coefficient was evaluated directly from the Fourier analysis equation as 1 over t, and was shown to be identical for all k. So we can use these Fourier coefficients to evaluate the Fourier coefficient for qt, okay, and let's use the properties that we are going to use is again the same. There are two terms, so you can use linearity, and for the first and second terms, and then they are shifted by t1. So again, let's use the time shift property. So qt is again xt plus t1 minus t1. That means in terms of ak, since ak is the Fourier coefficient of xt, okay, then this becomes ejk omega naught t1, okay, because of the shift. So xt minus t naught, you remember, xt minus t naught is simply implies that the Fourier coefficients will be e minus j k omega naught t, okay, omega naught t naught into ak. So all we are doing is that we know what is the Fourier coefficient of x. So we are using those Fourier coefficients and properties of Fourier series to evaluate the Fourier coefficients of qt, which are bk's. So this becomes e jk omega naught t1. Then we have e minus jk omega naught t1. Okay, this is minus, so there's a minus sign, there's a plus sign, so there's a sign difference. This is plus and this is minus. Substituting for ak, we can write this as 1 over t, and then you can combine two exponentials into a sign term like this. Okay, this becomes 2j over t. So finally, qt is also from the derivative. So you should recall qt is the derivative of gt. So we can use the differentiation property over here. Bk's, which are the Fourier series coefficient of qt. So d by dt can be written as j k omega naught. Okay, this is simply j k omega naught. Then whatever is the Fourier coefficients, okay, ak. For example, for gt, the Fourier coefficients was bk. Okay, so you have to substitute that as over here. So finally, for qt, the derivative of gt, we can use the differentiation property. Then you have jk omega naught and ck, which happens to be the Fourier coefficients of gt. Okay, over here, the Fourier coefficients of gt are ck, not bk. So this is ck. So if you use the differentiation property, you can find the Fourier coefficient of the square waveform. Okay, so what we have done is we evaluated first the Fourier series coefficient for xt, which were 1 over t for all k, and then for qt, which was expressed in terms of xt, as shifted impulses, we evaluated the Fourier series coefficient of qt from linearity and time shifts. Okay, as such, okay, this is for this bk, the Fourier coefficients of qt, and then there's a relationship of differentiation between qt and gt. Okay, so qt is the derivative of gt, so we can use the differentiation property. So bk's are nothing but, so this can be written as jk omega naught ck. Ck's are the Fourier coefficients of gt. So you can express from ck, okay, in terms of bk, you can write this as ck is equal to bk over jk omega naught, and we already know what bk is. Okay, so bk is 2j over t, sine of k omega naught t. So just bring k omega naught t over here. So for k not equal to 0, we have the coefficients for gt, which was the square waveform for one period. Okay, so we can determine by inspection the coefficient c naught for k equal to 0. Well, that's quite straightforward. If you look at gt, the period is from over one interval. You can take from minus t by 2 to plus t by 2, and then since you're taking the average, so this is gt dt. The average occurs over one period, that is 1 over t. That's the average of the signal gt, and this also happens to be the coefficient c naught. So you can see for gt from minus t by 2 to plus t by 2, well, this is non-zero over minus t1 to plus t1. So this is equal to, well, you can have this from minus t1 to plus t1, over which the signal is non-zero. Okay. and this becomes twice t1 over capital T. Okay, so this is the case over here. This is the average. So C naught is 2t1 over t, and you see this relationship of this ck over here is quite similar to what we had earlier for a square pulse like this. I mean the square pulse of a kind like this xt, for which we had the Fourier coefficients of ak were of this form. It was assigned by, it's like a sinc function. Okay, so ak's are taking the form of a sinc function, and you're having a very similar expression over here. So it's again a sinc function over here for ck's. Okay, so you see what we have done is we have used the Fourier series to come back to the same conclusion or the same Fourier series coefficients, and we have not used the direct Fourier analysis equations. So the evaluation of the Fourier series coefficients for delta t were quite straightforward. And then if you go back and just use the Fourier series to your convenience to derive the relationship between the qt signal, which was the again a periodic square waveform with alternate sign strengths impulses, and then from there you can you had the relationship with the square waveform. You can get to the Fourier series coefficient just by Fourier series coefficient of a square waveform by just plotting the series, and you have the same formation, same sinc form of the Fourier series coefficients for the square wave. Okay, so we have just used the Fourier series properties. This is yet another example, 3.9, a bit more involved than 3.8 and 7. So 6, sorry, we have considered 3.8 and 3.6. 3.7 is not clear. Okay, so again 3.9 is from your course text, Oppenheim and Shepard. What it says is, suppose you are given the following information, following facts about the signal xt. So the first fact says that xt is a real signal. Okay, this should imply that ak's are also real. Okay, then the fact 2 says that xt is periodic with period t equal to 4. That means it should be representable in terms of Fourier series. Fine. Okay, so it has a Fourier series coefficients ak's. Fine. So we are given the period, and we know that xt is real from the first two facts. Then the third fact says that ak is 0 for mod k greater than 1. That means there are 3 non-zero Fourier series coefficients, which means you just have, okay, this implies that there are non-zero 3 coefficients, which are a naught, then you have a minus 1, then you have 3 non-zero coefficients are a minus 1, a naught, and a1. That's it. This is the set corresponds to the Fourier series. This is the non-zero set of Fourier series coefficients. Otherwise, ak's are 0. Okay, and since the xt is real, so we can also say that a minus 1, a naught, and a minus 1 are real numbers. Okay, so then your fact 4 says that the signal Fourier coefficients bk equal to e minus j k pi by 2. A minus k is odd. If that is the case, then the bk, the Fourier coefficient to which it corresponds, I mean the signal, if the Fourier coefficients are odd, the signal is also odd. Okay, and you can see that this bk is written in form of e minus jk pi by 2, jk pi by 2, and then there is a minus k over here. So that means okay, this is your bk. That means your signal is not only time shifted. Okay, so here minus jk, yeah. So it's also there's also time reversal. Okay, there is a time reversal, and then there is a shift. So it implies a signal like this. This is not only xt minus 1, but I will rather have this at minus t minus 1. Okay, there's a time reversal as well. So this is what it implies. And then finally, you are given the energy of the signal. Okay, so energy of the signal is half. Okay, or 1 period, right? So these are 5 facts. So let's see if we can use these facts to find out what the signal is. So let us show that this information is sufficient to determine the signal xt within a sign factor. Okay, we are going to know what the sign of the signal is Okay, so to that precision, we're going to have this information is sufficient to determine xt. Okay, now according to fact 3, first of all, xt has at most 3 non-zero Fourier series coefficients, AKs, a0, a1, and a minus 1. Then xt has a fundamental frequency of omega naught 2 pi by 4, so it follows, which you can see over here as well, it's 2 pi by 4 to pi by 2. And xt is, since it's periodic and there are 3 non-zero Fourier coefficients, you can expand it in terms of Fourier series. So you're going to have a minus 1 e minus j omega naught t a naught a1 e j omega naught t. Now since xt is real, from fact 1 we can use the symmetry property to conclude that a naught is real, and therefore ak is a minus star k, okay, because it's real. So complex conjugation is not going to matter over here. So what you can do is you can combine a minus 1 with a1. So consequently, you can write this as such. All the quantities, all the Fourier series coefficients are real over here. You can combine the two exponentials. A minus 1 is a1. Okay, so from this fact, yeah, a1, this simply implies that a1 is a minus 1. Okay, I'm not going to put a conjugate because it's real, so conjugate is not important. So therefore, you can a minus 1 is the same as a1. So you can have this a naught 2a1 cosine 2 pi by t. Okay, this is your signal for now. So these we have used how many facts? 2 facts, basically 3 facts. Okay, we know what the period is, so we have expanded this in Fourier series coefficients, and then we know there are 3 non-zero Fourier series coefficients, and xt is real. So, but we don't know what a naught and a1 is, but xt is going to take this form of a sinusoid. Okay, that's all we know. Now, let's use the fact 4 and 5 that the signal Fourier coefficients, signal with Fourier coefficients which is shifted is odd. So let us now determine the signal corresponding to the Fourier coefficients bk given in fact 4. So using the time reversal property, we know that a minus k subscript a minus k correspond to the signal xt. Okay, so if you recall that xt, if you recall the time reversal property was if xt has the Fourier coefficients of ak, then if you time reverse, okay, if you flip the signal around the vertical axis, so it becomes x minus t, it will have the Fourier coefficients of a minus k. So this is what a minus k is. This is subscript. Okay, so you can write this as a minus k. This is what it implies. So also the time shift property indicates that the multiplication of the kth Fourier coefficient by e minus jk pi by 2 is e minus jk omega naught, which corresponds to the underlying signal being shifted by 1 to the right. Okay, so e minus jk pi by 2, so the period is 4. T naught is 1, you can see over here. T naught is 1, it simply means that the signal is shifted by 1. So having t replaced by t minus 1, we conclude that the coefficients bk correspond to the signal, x minus t. Okay, so much ink. Anyways, x minus t minus 1, x minus t. So because there is a time reversal, if you look at this Fourier series coefficient, you see the time reversal as well, and then you also see there is a shift of 1 second to the right. So this is xt minus 1, and then there is a flipping of the signal as well around the vertical axis. So this forms x minus t plus 1. And this is the odd signal. This is an odd signal. So bk is, if the coefficients are odd, the signal is also odd. Okay. So which corresponds to the fact 4 that must be odd. So this is my x minus t plus 1 is odd. Since xt is real and x minus t plus 1 must be odd and real. Okay. But xt is real, but x minus t plus 1 is odd, it must also be real. So it's odd and real. The Fourier coefficients of x minus t plus 1 must be purely imaginary and odd. Alright. So if you recall that for an odd signal, xt, if xt is odd, I mean this is, I'm just taking an example, xt is real in this case, but if xt is odd, then it is also written as x minus of minus t, right? So this simply implies from the first insight is that expression, you can say that x0 is 0. You can have nothing. You don't have a non-zero value at t equal to 0. Okay, I mean x0 is equal to minus x of 0 simply implies that x 0 is 0. Okay, so thus B naught is 0. Okay, so this coefficient, if this BK coefficients are odd, then B naught is 0. B naught is supposed to be 0. And B minus 1 is B minus 1. So B of 1, B minus 1 is B1. Okay, B1. So they're odd. So since the time reversal and time shift operations cannot change the average power per period, then fact 5 holds that if xt is replaced by x minus t plus 1, then the power will still going to be half. Okay, I mean, if you're even going to shift in time, the power is not going to change. The power is still preserved. So this is half. So that means that also implies, well, you can write this as such, since b naught is 0, and this implies that b1, the power in the harmonics, will be the power in the signal itself, right? So this is b minus 1 whole squared. This is equal to 1. This is equal to half, right? So you can say that b1 is if it is imaginary, this is j by 2. Or if it is real, this is 1 over 2. Okay, but since the Fourier coefficients, they must be purely imaginary and odd, then it will be j by 2, right? So if you use the Parseval relation to conclude that the power in the Fourier coefficients is also the same as the signal power, then substituting b1 as minus b1 in this equation, as you have seen earlier, okay, b minus 1 is b1. So if you substitute that, you're going to obtain that b1 magnitude of b1 is half, right? So 1 over 4 plus 1 over 4 is 1 over 2. Basically, this is twice magnitude of b1 mod square is half. So that means, okay, so you're going to take the square root, so magnitude of b1 is 1 half, right? So b1 mod square is 1 quarter, so b1 is half. Since b1 is also now to be purely imaginary, then it must be either plus minus j by 2, right? Now we can translate these conditions on b0 and b1 into equivalent statement on a0 and a1. First, since b0 is 0, fact 4 implies that a0 is 0. Okay, so the fact 4 is that a signal with Fourier coefficient is as such, it's odd. So if b0 is 0, well, it also implies that a0 is 0. Okay. Then we are left with a minus 1 and a plus 1. So with k equal to 1, this condition implies that a1 is e minus j pi by 2 b1, which is minus j b of minus 1 jb1. Okay. So thus, if we take b1 as j by 2 and a1 is minus 1 over 2, then xt is minus cosine of pi t by 2. Okay, how it's coming? Because a0 is 0 over here now. It's b0 is 0. It's b0 is 0, a0 is 0. So you have twice a1 cosine of pi by 2. Okay, so a1 could be either minus 1 by 2. Okay, because if we take b1 as j by 2, then a1 is minus 1 by 2, and this corresponds to minus cosine pi t by 2. Alternatively, if we take b1 as minus j by 2, then a1 will be 1 over 2. Okay, I mean, because you see this is minus jk pi by 2, right? So this is in terms of b case, if b1 is minus j by 2, then a1 becomes 1 by 2, which means xt is cosine pi t by 2. So you see, up until the sine factor, we have evaluated xt. These conditions are sufficient to understand what xt is. So from the first three facts, we concluded that xt was of the form sinusoid. Okay, it was a sinusoid form with a dc term. The dc term is 0 because in fact 4, bk is an odd signal. Bk refers to the Fourier coefficient of an odd signal, and for an odd signal, x0 is 0, right? So a0 becomes also 0 at that time. So a0 is also 0. Okay, because if b0 is 0, then this factor is non-zero, so a0 is 0. So the DC term is gone. Then you're left with a1. Okay, so a1 implies, so since we also know that this is odd, so b1 is minus b1, right? And from the power, it's either j by 2 or minus j by 2. Okay, so if b1 is j by 2, then a1 is minus 1 over 2. Okay, because if you are going to multiply your factor over here, minus j pi by 2 is minus j, right? Plus j pi by 2 is plus j. So it makes the a case as real, it makes AK as real. So this is this B, okay, this BK equals, since K is 1, so let's write this as B1 as minus J pi by 2, and we have this as A minus 1, and we also have B minus 1 as EJ pi by 2, multiplied by A1. So you see you can directly evaluate A1 and A minus 1, right? Because this EJ pi by 2 is J, right? And B1 and B minus 1, well, this B1 can be plus minus J by 2, okay? B minus 1 can be the other sign, minus J pi by 2. So you can just go ahead and evaluate A1 and A minus 1 from that, and then substitute over here. So this becomes 1 over 2, and then either you can have cosine pi t by 2, pi by 2t, or minus cosine pi 2 by t. Okay, so all it depends on, if you take B1 as J by 2, then A1 is minus 1 over 2. Alternative, if B1 is minus J by 2, then A1 is 1 over 2, and then that makes xt as cosine pi t by 2. Okay, so all we have done is, based on all these facts, we understand what the properties are and what are the Fourier series coefficients. And these Fourier series coefficients are enough to construct the original signal. Okay, that was the idea behind the example. That's all.